This is the 14th lecture on signals and systems, and today's lecture shall deal with more properties of the Fourier transform in continuation of the previous one. But before that, I would like to do one interesting example which one of the students yesterday pointed out in the class, and since it involves a little more consideration than what we have been doing so far, I thought I'd do it in the general class. I have also requested the other section to do this problem. The problem is 316C of the textbook, and the the question is this, that we have an x of t which is applied to a system like this, a delay, another delay, and so on, many delays, and each delay is capital T. That is, if I feed x of t here, then what I get here is x of t minus capital T. That's what it means. And then signals are picked up from each of these outputs, multiplied by capital T, and then added together. The multiplying constant is capital T, and then they are added together, two at a time. This is how it is done in the computer or in any other digital hardware, two at a time. And so this continues, and ultimately after infinite number of such delays, well, the number is not specified, so we take this as infinite number. The output is y of t, and obviously the relationship between y of t and x of t is that y of t is t times x of t plus t times x of t minus t, t minus cap t, then capital T times x of t minus 2t, and so on. And therefore it is t times x of t minus kt, where k goes from 0 to infinity. Is it obvious, this relationship between the input and output? All right, this is obvious. The question now is, in this, if capital T goes to 0, if capital T tends to 0, what happens to y of t? What happens to y of t? Tends to some y0 of t, which if you just look at this, you see it should be 0 because it's multiplied by capital T, but that's not the case. We'll find out what y0 of t. In addition, what is given is that x of t is e to the minus t ut. If that is the case, then what is the shape of y of t for a general capital T which is greater than 0? The shape of y of t. These are the two questions, and then there is a third part which I shall come to later on. Is the question clear? Okay. Now y of t is summation capital T x of t minus kt, k equals 0 to infinity, and x of t is equal to e to the minus t u of t, and therefore I can write this as k equals 0 to infinity capital T e to the minus t minus kt u of t minus kt. All right. And if I want to write this explicitly, well, it is t e to the minus t plus t e to the minus t minus t u of t minus t, and so on. I am writing this in an expanded form to have a physical picture more clear. All right. If I plot this now versus t, what is happening is, for the first term, this is multiplied by u of t. For the first term, it starts at capital T and goes like this. The second term, let's use other colors. The second term starts at capital T and it goes like this. And you have an infinite number of such signals. what you have to do is to add all of them up. If you add all of them up, obviously your signal will come like this. For the first part, 0 to t, it will come down like this, and then here there will be a jump by an amount capital T. So it will rise like this, then it shall fall like this. It will not be quite this, because there is this blue curve also adds to it. So it will fall like this up to this. Then again there will be a rise of capital T, and it will go like this. Then again there will be a rise of capital T, and so on. And this shall continue. Alright, so it will be a rising curve, the peaks of which, if you draw them, it will be a curve like this. The peaks gradually increase in height. This is the shape of y of t in the general case when capital T is not constrained. Capital T is not constrained to become infinitesimally small. Now let capital T become infinitesimally small. Let us see what happens. What will happen? These ranges will become very narrow. If capital T tends to 0, we can take capital T as a dt or d tau. This will become very narrow. So what you will be able to observe is only the peaks of this curve. That will form a smooth curve, as you shall see. And for this we start with the same expression, yt is summation capital T x of t minus kt. Well, k goes from 0 to infinity, which is k equals 0 to infinity, capital T e to the minus t minus kt, u t minus kt. Alright, now we do some interesting things. Our capital T tends to 0. Capital T tends to 0. So what we do is, well, we put two dots here. Capital T tends to 0, so put capital T equal to some quantity d tau, infinitesimally small. Alright, then obviously k times capital T will be equal to tau. Alright, because an increment in kt is capital T, and capital T you have put d tau, so kt must be equal to tau. And when t tends to 0, obviously the summation loses the meaning. Please say this again. Okay. What we have said is capital T tends to 0, so we put capital T equal to d tau, an infinitesimally small quantity. Now, when I multiply by k, which is an integer, k times t, obviously this has to be tau, because the increment in kt is k plus 1t minus kt is equal to capital T, and capital T is d tau, and therefore kt must be equal to tau. That is a number of such infinitesimals added together that makes a non-infinitesimal quantity equal to tau. Tau is a running variable. Tau goes from, k goes from 0 to infinity, so tau goes from 0 to infinity. Alright, and then the summation loses its meaning, and therefore what we get is, you take these two ends and pull it out, straighten it out, so you get an integral. Y of t, integral will be from 0 to infinity, t will take care of d tau, then e to the power minus t minus tau, and u of t minus tau. Alright, obviously because of the occurrence of u of t minus tau, the upper limit shall now change to t, not tau, because the tau is the dummy variable integration, and then this can be forgotten. Alright, so our integral therefore becomes yt equal to integral 0 to t e to the power minus t minus tau d tau. Yes, and this you can easily see that this is equal to, well, 1 minus e to the minus t. Right? this happens only after t equal to 0, and therefore you must multiply this by u of t. So when capital T tends to 0, y of t does not become identically equal to 0, it rises in an exponential manner like this. It rises from a value of 0 to final value is 1, and this represents the peaks of that sawtooth shaped curve. The curve now becomes an absolutely smooth curve because capital T has gone to infinity. The last part of the question says, well, we call this y0t, alright, that is the output when capital T tends to 0. The last part says that for any t greater than 0, you have to show that yt envelope, for any t greater than 0, yt envelope, by envelope I mean I have the rise is like this, the envelope is this curve, that is this curve. The envelope has discrete values because it only joins the peak, so your envelope is valued at t, 2t, 3t and so on. The question says, slightly involved question, you have to read in between lines. The question says that yt envelope is given by capital T divided by 1 minus e to the minus t y0 t plus capital T. Now there is a slight problem in understanding the problem. Envelope means that if you can, what you have to show is that at a general value of small t, let's say nt, the envelope is valid only at integral multiples of capital T. So for a general value of nt, you have to show, that is to show that y of nt shall be equal to capital T divided by 1 minus e to the minus t y0 of n t plus t, that is y of n plus 1 t. This is what has to be shown. Alright, and to do this we recall that y of nt shall be equal to summation capital T e to the minus t minus kt u t minus kt. This is my general formula. K equals to 0. Up to what value of k should we go? Because we are finding out the function at nt. Obviously we should go up to n only. Alright. Now let's write this in an expanded manner. Capital T we take out. Let's write this in an expanded manner. What we get is t, no t, e to the minus nt when k equals to 0, plus e to the minus n minus 1t plus etc. plus e to the minus t. When k equal to n, we shall get a value of 1. Alright, and therefore this summation is simply capital T 1 minus e to the minus n plus 1 t divided by 1 minus e to the minus t. Alright, this is a geometric series, I have summed it up. So this is equal to capital T divided by 1 minus e to the minus t. Now if you recall, y0t, that is when capital T was tending to 0, y0t was 1 minus e to the minus t. And therefore the upper term, the numerator term, I can write as y0 of n plus 1 t. And so I have proved it. Alright. Do you know the meaning of this, QED? Okay, that's good. I didn't know for a long time. I had to find out from a Latin dictionary. Okay, is there any question regarding this problem? If not, then we go to the other properties of Fourier transform. let's recall that if x of t is Fourier transformable, then the relationship is that x of omega is equal to integral minus infinity to infinity x of t e to the minus j omega t dt, and the inverse Fourier transform is given by 1 over 2 pi minus infinity to infinity capital X of omega e to the power j omega t d omega. Last time what we showed was that if x of t, one of the properties that we had proved was that if x of t is real, then capital X of omega, complex conjugate of this, is equal to capital X of minus omega. This is what we proved. Now we start with this property today, that if x of t is real and even, if x of t is real and even, then capital X of omega is purely real. The spectrum, the Fourier transform, is purely real. The proof is extremely simple. X of t is real and even. Alright, let's see. If x of t is real and even, then x of omega in general is minus infinity to infinity x of t e to the minus j omega t dt. Now x star of omega, which is equal to x of minus omega, is given by where do I bring x of minus t? Okay, is given by integral minus infinity to infinity x of t e to the power j omega t dt. Now let's put t equal to minus tau. Let's make this change of variable. Then this integral becomes x of x star of omega becomes equal to minus infinity to infinity. No, let's see what the limits become. X of minus tau e to the minus j omega tau, then we shall have minus d tau. The minus sign goes here, and so the minus sign can be converted to a plus sign if we change the integrals. In other words, it simply becomes this multiplied by d tau. Alright? So, but my x of tau, x of t is even, and therefore this is the same as x of tau. So this is the same as x of tau, minus infinity to infinity x of tau e to the minus j omega tau d tau, which is the same as capital X of omega. Alright, is this clear? Very simple transformation, and then I prove that the complex conjugate is the quantity itself, so the quantity must be real. In a similar manner, you can show that if x of t is real and odd, if x of t is real and odd, then x of omega is purely imaginary. Is purely imaginary. Now, this leads us to a very simple formulation, that is, for a general x of t, which is neither purely even nor purely odd, for a general x of t, you know, you can always break it up into even part and odd part. And if this is real x of t, you can always break it up into even and odd part. And so if you take the Fourier transform of this, then the Fourier transform can be written in terms of its real part plus its imaginary part. Any Fourier transform in general can be written in terms of its real and imaginary parts, and you can see that the even part must transform to the real part of the spectrum from the property that we have just discussed. X e of t must have a Fourier pair with x r of omega. Is this clear? Similarly, x o of t must have a pairing with x j of omega. alright. XO of t transforms to what? Does it transform to xj? J times xj. This must be remembered, okay. It transforms to a purely imaginary quantity. So the coupling is between this and this and this and this. This fact sometimes simplifies analysis and synthesis problems tremendously, and we shall see examples of this later. Next we come to delay. That is, if x of t, delay or time shift, it could be advance also, delay or time shift. If x of t forms a pair with capital X of omega, then the question is, what is x of t minus t0? What is the Fourier transform of this? And from the definition itself, that is minus infinity to infinity x of t minus t0 e to the minus j omega t dt, you can make a transformation from t minus t0 to, let's say, tau. Then t becomes tau plus t0, dt becomes d tau, and you can easily see that this would be simply e to the minus j omega t0 capital X of omega. The sound is being picked up. So this is the relation. If you have a time delayed signal, this would be very important in our work in the future further properties. If a signal is delayed by an amount t0, all that happens is that the Fourier transform gets multiplied by an exponential e to the minus j omega t0. The question, what happens to the amplitude spectrum? Nothing happens, because the amplitude of e to the minus j omega t0 is 1. So only thing that happens is the phase spectrum gets modified by a linear term, that is the phase of x, let's call this x1, okay, let's call this x1, this transform as x1, phase of x1 becomes phase of x minus omega t0, and therefore a linear phase term, it's proportional to omega, a linear phase term is added to the phase of the previous spectrum. The magnitude spectrum remains intact. Then you consider the property of differentiation. This is rather easy to see. If you look at x of t, the definition minus infinity to infinity, I beg your pardon, capital X of omega. No, we'll take x of t. You take x of t is the inverse Fourier transform, 1 by 2 pi minus infinity to infinity capital X of omega e to the j omega t d omega. Alright. Now if you differentiate both sides, what I want to do is, how is dxt dt Fourier transform related to capital X of omega? That's what I want to do. Now as far as this integration is concerned, the variable is omega, and therefore I can differentiate with respect to time inside the integral, and what we get is 1 over 2 pi j omega x of omega integral minus infinity to plus infinity e to the j omega t d omega. And it is obvious that the Fourier transform pair of dxt dt is j omega x omega. Alright. So x prime or x dot t is the pair of j omega x of omega, and by a very similar argument you can see that x2 dot of t shall transform to minus omega squared x omega, and so on. You can differentiate any number of times, and then all you have to do is to put the multiply capital X of omega by the required power of j omega. The problem arises when you take the integration of a signal. That is, the question is, if x of t forms a pair with capital X of omega, what is minus infinity to t x tau d tau, what is the Fourier transform of this? integral. Now if you recall that x dot of t takes to j omega x of omega, it is very tempting to say that integration after all is the reverse process of differentiation, and therefore what we should get is simply x of omega by j omega, reverse process. But unfortunately this result is incorrect, and why it is incorrect will be the topic of discussion for the rest of the class. It's a very involved question and you must follow me very carefully. We proceed like this. We leave aside the question of integration for a moment, all right? We leave it, we leave aside. We look at convolution first. Convolution. That is, if you have a signal y of t, which is the convolution of x of t star h of t, which is the general question of a linear system, that if you know the impulse response, if you know the input signal, then you know the output signal. And suppose the corresponding Fourier transforms are capital X of omega and capital H of omega. Let the Fourier transform of capital Y of t be Y of omega. Then we ask the question, how are they related? And you shall see that what is convolution in the time domain is simply multiplication in the frequency domain. It's as simple as that. Convolution involves integration, and this integration is replaced by simple multiplication in the frequency domain, and that is the heart of popularity of Fourier transform. Alright, Fourier transform converts the problem of differentiation and integration into problems of simple addition and simple multiplication and division. That's all. Now to prove this, the proof is not very difficult if you proceed carefully. The Fourier transform of y of t is defined as minus infinity to infinity y of t e to the minus j omega t dt, and y of t in turn is given by the integral, that is minus infinity to infinity x of tau h t minus tau d tau. Now let's substitute this here. Such tricks shall be exercised many times, so please do follow this carefully. Minus infinity to infinity, we had then another integral minus infinity to infinity x of tau h t minus tau d tau. All right, this is my y of t. Then I multiply by e to the minus j omega t and dt. Now we argue that in this integration there are two integrations. It's a double integration. There are two variables, t and tau. Both of them are dummy as far as integration is concerned, because the value of the integral is in terms of omega. Omega is the variable. Why are they dummies? Because both of them are definite integrals, minus infinity to infinity. So the variables drop out. These two variables are not related to each other. They are not dependent on each other, and therefore I can write this in this form, minus infinity to infinity. Let's first integrate with respect to t, small t. Then x of tau, let's take it out, and minus infinity to infinity h of t minus tau e to the minus j omega t dt. First integrate with respect to t, then with respect to tau, d tau. And if you look at this integral, isn't this simply the Fourier transform of h of t minus tau? And for a time shift, we have already seen that this should be equal to h of omega multiplied by e to the minus j omega, not t, tau, h of omega e to the minus j omega tau. All right. Now if I substitute this, then I get capital Y of omega as equal to minus infinity to infinity x of tau. This integral is h of omega e to the minus j omega tau, then d tau. and therefore I get h of omega. H of omega I can take outside the integration. We get minus infinity to infinity x of tau e to the minus j omega tau d tau, and this is precisely capital X of omega. All right. Therefore, this is h of omega times capital X of omega. We have therefore established this very interesting relationship that what is convolution in the time domain becomes multiplication in the frequency domain. This is the first result. Our ultimate result is to obtain the Fourier transform of integral of x of t. First step is we prove the convolution property, that convolution transforms into multiplication in the frequency domain. Then we look upon, now we go back to the integral, that is minus infinity to t x of tau d tau. I can look upon this integral like this, minus infinity to upper limit, we will keep it flexible now. What I will do is, I will multiply by u of t minus tau d tau. All right. Then that is to take care of the upper limit as small t, we are bringing in a u of t minus tau, and then I can write this as infinity. Is that clear? Are these two integrals identical? Yes, because u of t minus tau is 0 for tau greater than t, and therefore this integral is equivalent to this. And if you look at this, don't you see that this is the convolution of xt and ut, and therefore if this is my y of t, if the integral of x of t is y of t, then capital Y of omega is simply x of omega multiplied by u of omega, where u of omega is the Fourier transform of u of t, the unit step function. The unit step, therefore the problem that remains now, what we wanted to do is to relate y of omega to x of omega, and our temptation was that it must be x of omega divided by j omega, and we said that is a wrong conclusion, it is not true. So what remains to be done is to find out the Fourier transform of u of omega. Question is u of t Fourier transformable? It neither satisfies the energy condition, it is not an energy signal, nor does it satisfy Dirichlet conditions, because it is not absolutely integrable. The absolute integration goes to infinity. But one must remember that these conditions are sufficient conditions, not necessary, and therefore we may be able to do this. Let us see if we can do this. U of t. So the problem now is to find out what is u of omega, if at all we can integrate. Let us recall the definition of u of t. U of t is 0 for t less than 0 and 1 for t greater than or equal to 0. This is my u of t versus t, and this is 1. Now u of t, let us write this u of t as u e of t even part plus u o of t. All right. Then can you find out what is u e of t? It is u of t plus u of minus t divided by 2, and therefore what is the value? This is half for all t, isn't that right? This is half for all t. U o of t is u of t minus u of minus t divided by 2, and therefore it is equal to minus half for t less than 0, half for t greater than 0. At t equal to 0 there is a discontinuity. All right. Let us look at these two functions. U e of t versus t, and that is simply this, half for all values, and u o of t is minus half and then plus half, half minus half versus t. Alright, these are the even and odd parts of UO, the unit step function. Now let's look at the odd part first. Alright, if we can transform the even part and the odd part separately, it's a linear, the Fourier transformation is a linear process, and therefore I can simply add them up. Let's look at the odd part first. Suppose you differentiate the odd part, u prime of t. What is the result? What is the result? It's simply a delta t. Isn't it right? The differentiation here is 0. Here it is 0. It exists only at the point of discontinuity, and the discontinuity goes from minus half to plus half, and therefore the differential coefficient area under that curve shall be equal to 1. It's a jump from minus half to plus half, and therefore this is precisely delta t. Alright, if that is so, u0 prime t is equal to delta t, then obviously the Fourier transform of both sides, u0 prime t, shall be equal to what? What is the Fourier transform of delta t? Pardon me? Fourier transform of delta t, we have proved this. What is the value of the constant? Okay, Fourier transform of delta t is 1. Now, therefore, the Fourier transform of u0t, what will this be equal to? This will be 1 by g omega. Isn't that right? Fourier transform uO of t would be equal to 1 by g omega. Let's call this uO of omega. Is this clear? Fourier transform of differential coefficient is g omega times the Fourier transform of the original function. Therefore, this is equal to 1 by g omega. Now let's look at the even part. Fourier transform of the even part, ue of t. Yes.
So you have used the fact that you said was not correct earlier.
What was not correct?
1 upon j omega.
Oh, we have used the fact that x dot t, if x of t transforms to capital X of omega, we are not using the integration, we are still using differentiation. For differentiation this is true, x dot of omega is the pair of j omega x omega, and therefore what we have done is Fourier transform of this should be equal to j omega times uO of omega, and therefore uO of omega is 1 by j omega. I have not used integration property, no, it's a differentiation property. Now let's look at the other part. This is the Fourier transform of half. E of t is half for all values of t, and we also know that the Fourier transform of e to the j omega naught t, what is this equal to? 2 pi delta omega minus omega naught. Now can I use this result for deriving this? Fourier transform of 1, if you put omega 0 equal to 0, Fourier transform of 1 would be 2 pi delta omega. So the Fourier transform of half shall be pi delta omega. Is that okay? Yes? Or there is a hitch somewhere? There may be. Well, let's take it for the present. Fourier transform of half, which is equal to small u of ue of t is equal to pi delta omega, and therefore the Fourier transform of the total quantity u of omega should be equal to the Fourier transform of the even part, that is pi delta omega plus 1 over j omega. Alright, this is a very, very important result. The Fourier transform of a unit step function, it does not satisfy the sufficient conditions for existence of Fourier transform, but there exists a Fourier transform which contains an impulse in the frequency domain, delta omega. Shall we now go back? He had said that if y of t is equal to minus infinity to t, x of tau d tau, then y of omega is x of omega times u of omega, because we had shown that y of t is a convolution of x of t with u of t, and by convolution property we have seen that y of omega is the product of the two transforms. So our finally therefore minus infinity to t x tau d tau transforms to x of omega multiplied by u of omega, which is 1 over j omega plus pi delta omega. This result can be written in various forms, but one of the popular forms is x of omega by j omega. This is what is the temptation from the differentiation theorem. The temptation is to take only this term. However, because of the discontinuity in the unit step function, there is a delta function and it is written as pi. Now if I multiply x of omega by delta omega, x of omega, omega can be replaced by 0, because the function exists only at omega equal to 0. So pi x of 0 delta omega, and this is what the result that we wanted to establish, minus infinity to t x of tau d tau. We have done it in several steps, and that was necessary. From common sense or from routine calculation, one is apt to ignore the discontinuity, and if you ignore, it's like driving a car on a very rough road. If you ignore the potholes, then you had it, you have a jerk. Here the result would be disastrous, your result would be absolutely wrong. This delta omega plays an extremely important part, because of wherever there is a discontinuity, the transform domain or in the time domain differentiation, the delta functions are bound to come, and this is why delta functions are a fact of life as far as electrical engineers are concerned, and I include computer engineers amongst electrical engineers, because well, one gave rise to the other. Alright, the last property that we shall discuss today is frequency. Well, first we discuss time scaling. That is, if we are given x of t as the pair of x of omega, what happens if t is multiplied by alpha, let's say, x of alpha t? What is this equal to? You recognize that depending on the value of alpha, this is either compression or stretching, compression or dilation. Alright, now what happens to this? First let us assume that alpha is positive. You will see that the result is independent of whether alpha is positive or negative, but first let us establish this for alpha positive. Then the Fourier transform x of alpha t is minus infinity to infinity x of alpha t e to the minus j omega t dt, and we assume that alpha t is equal to tau. Then t becomes, this t is to be replaced by tau by alpha, and dt is to be replaced by d tau over alpha, and therefore this integral becomes 1 over alpha, alpha can be taken out, 1 over alpha minus infinity to infinity x of tau e to the minus j. This quantity I write this as omega by alpha, alpha I bring below omega, then I multiply by tau, d tau, alright, and the result is written on the paper, not on the wall. Result is that if this is considered as a new frequency omega prime, then you notice that this quantity is simply capital X of omega prime, and therefore what we have established is that x of alpha t is the transform is 1 by alpha capital X of omega prime, but omega prime is omega by alpha. And however, if alpha is negative, then the result, the derivation slightly is to be done carefully. Alpha is negative, then I have the same integral minus infinity to infinity x of alpha t e to the minus j omega t dt. Now alpha is negative. As usual, we put this we put alpha t as equal to tau. Then this t goes to tau by alpha and dt goes to d tau by alpha. Now we have, I can take 1 by alpha out, but the problem now is because alpha is negative, the sign, well, because alpha is negative, the integration limits change, that is from plus infinity to minus infinity, and the only way I can bring to minus infinity to plus infinity is to take a negative sign, is to introduce a negative sign. If I insist on writing the limits like this, then I must bring a negative sign. That means I must use a minus alpha here. Is that okay? Which means that my result would be 1 by mod alpha. Is this point clear? So what we get is x of tau e to the minus j, again omega by alpha tau d tau, and this is therefore 1 by mod alpha capital X of omega. And so I can now, is the point clear? Omega by alpha. Thank you. Now, in view of this, that is alpha greater than 0, alpha less than 0, you see the result is identical, except that what you have to do is to put a mod sign here. That is, whether alpha is positive or negative, this would be valid. Not inside, one must remember this, not inside the argument of capital X. In the next class, we shall take some more properties of Fourier transforms and work out a very large number of examples. Large number means in 1 hour we can do 2 or 3, and that's what we will do.